All right, this is our project. In this project we are doing a study on model airplanes and different designs and materials that they are made out of. Paper airplanes are a simple and fun form of entertainment that take many sizes and shapes and can be made on almost any flat and malleable material. But what kind of paper airplane flies the furthest, and what material can you use to maximize the distance it flies? In this experiment, various types of paper planes with different materials will be tested to see what type of material and model makes the furthest flying paper airplane. There are several different factors that affect the distance that a paper airplane flies. These factors are brought into consideration when performing the experiments, and to help mitigate these factors, the experiment was performed in the one of the SDFC basketball courts, and only one per plane, and only one plane per material and design was made to help mitigate human error from the actual folding process. Some other factors to take into consideration was the wind and air density, and this is why we did it in the FTFC. In terms of design, the design has several different factors that go into it, such as wing size, aerodynamics, fold quality, weight balance. And the material also takes into account with material density and shape retention, which we'll go into later in the errors and why this is a big factor. And another factor is how it actually launched. So the actual angle it was launched at, the launch height, and also the launch velocity.
All right, so our procedure involved creating one paper airplane for each factor combination of patterns or folding patterns and material. The next step was to find an environment that had no wind and enough room to let each paper airplane land without hitting any kind of wall or obstruction. In this case, we chose the SDFC. Next step was to set up a tape measure from the throwing line straight out into the basketball court. And next, for each plane, we took turns in the group launching the airplane with a rubber band at the baseline and tried to aim the rubber band along the tape measure to get a more accurate distance measurement. Next, we measured from the furthest point of the airplane when it lands and stops moving right over to the tape measure, and that is the distance measurement we recorded. The last step is to repeat this process for every combination of folding pattern and material of airplane.
Awesome. So this begins the data and analysis section. So we have the raw data section on the right-hand side that you can see. And then for the left, we just took some sample average data that's going to help us come to a conclusion when we do our ANOVA and t-test a little bit later. So to find if there's a correlation between the plane designs and between the plane material, MATLAB is used to make an ANOVA analysis between the two properties. Before running the ANOVA analysis, the correlation coefficient is defined as alpha is equal to 0.05. This is found to be quite in like a common industry standard value, and also is very reasonable considering the type of test that we're doing and the threshold value that we actually measured a little bit later. So we need to define the null and alternative hypothesis to use this type of analysis to perform this on the average data. So we chose this by making our null hypothesis, or HO, that there's no significant correlation between the material a paper plane is made of and the distance it flies. And then our alternative to that for the material was that there's a significant correlation between the material and paper plane that it's made out of and the distance it flies. It's just the inverse of the other. And it's the same exact style of null hypothesis for the design as well, that there's no correlation between the design of the plane and the distance it flies. And then also the alternative to that being that there is. So here were some of the ANOVA materials. The analytics are going to be in the next slide. This is a pretty cool design for this type of test, because if you picture yourself like overhead or towards the top of the plane looking down at the SCFC court, you can actually see the upper and lower quartile and mean values for where the plane had actually ended up landing, which is pretty neat. So we can see that there's quite a lot of variance for design, and there's a lot less variance for material, which we'll talk about a little bit later.
These are our two ANOVA tables. The top one is for the material, bottom one's for the design. These tables show the calculations used to determine the p-value to see if HO could be accepted or rejected. For the material type, we got a p-value of 0.3609. Because our p-value is greater than A, we're going to reject the alternative hypothesis, which means there is no significant correlation between the material and the distance. However, for the design, we got a really low p-value, so it was greater, so we had to reject the null hypothesis. So in conclusion, there is a correlation between the design of the paper plane and the distance that it flew in our testing. Here, we show if there is a significant difference between different material types and design types for each character using a t-test.
So now we get into the conclusion. So with the data, it was shown that the material's null hypothesis is not rejected, meaning that there was no significant correlation between the material of the paper used and the distance it traveled. However, the null hypothesis for the design of the plane is rejected, meaning that there is a significant correlation between the general design of the plane and how far it traveled across the room. This can also be seen with the raw data shown previously in the data analysis section, how even though all different types of designs of the planes use different materials, they all stayed relatively in the same range of flight distances. And below, you can see an image of all the different planes that we used throughout the experiment.
Out of all, continuing the conclusion, out of all the planes we thrown through, Suzanne flew by far the furthest on average on pretty much any material. The Sea Glider, on the other hand, flew by far the shortest, often tumbling due to this imbalanced design. The best design depended on the plane. For instance, the Suzanne showed the best results with cardstock, and so did the Sea Glider, but it showed the worst results with notebook paper, while the Sea Glider performed the worst with printer paper. To our surprise, the foil material performed a lot better than we expected, and despite its flimsy construction and additional weight, it flew often the furthest on most designs.
So one of the biggest issues that we encountered during the experiment is that the plane, after we flow them, it get like the tip, it get a bit crushed. So that affect the performance of the plane on the next attempt. And if you keep repeating it, it get more deformed. If you check the picture we took, the aftermath of the experiment, you see that for a lot of the paper plane, the tip of it, it's like gone. Another issue that we encounter is that the tape that we use isn't long enough. So sometimes we have to take the measurement from the opposite side and subtract the total length of the cord, which can affect the result. Also, because the paper plane is very light, sometimes it wouldn't fly straight, but it would fly to the side, or it would just spin around, like do a barrel roll and then crash down, which affect the result. And because we're using the basketball court, sometimes we just launch straight to the hoop and mess up our measurement.
All right, that's a presentation. Thank you.